Hello Abaqus user, welcome to Abaqus Acumen for quick and sound learning. In today's session, we are going to discuss on how to do a aluminum pipe bending in a Abaqus standard. So in this particular session, you'll learn how to define a Abaqus contact, how to handle a material nonlinearity. Also, you'll learn how to handle a geometric nonlinearity. Also, you'll learn how to apply a follower force in this particular video. So right now on my screen what you are seeing a aluminum pipe which is clamped at one end, and there is a contact between a rigid mandrel and aluminum pipe, and the force is applied at the one end. So this is what we are going to perform. So the problem definition is aluminum pipe bending using a Abaqus standard. So we have a aluminum pipe which is a 1-inch dia and 1 millimeter thick. One end is clamp, and from the clamp end at 8-inch distance there is a 3.25-inch rigid mandrel is there, and then at the free end we are going to apply a force around 270 Newton. So the distance between the mandrel support to the force application is a 24-inch. So overall it is a 32-inch length, 1-inch diameter pipe. So the finite element modeling, what approach we are going to take, we are going to define a contact between pipe and mandrel. We are going to use a 3D shell for this particular problem, mainly a S4 we are going to use. This particular problem will have a elastoplastic material model, so that way we can have some hands-on and learning session on how to define a material nonlinearity. This particular is a quasi-static large deformation problem, so mainly this particular problem is formulated to handle a geometrical boundary and material nonlinearity. So to save everybody's time, we already have this mesh model, so we are going to start with importing a mesh model. In case you want to do a practice and you need this mesh model, just send an email at abaqusacumen@gmail.com. we'll send you the mesh model. Other part is for this particular problem we are going to use aluminum 6061 T6 alloy metal property. So the typical modulus is a 72 GPa, Poisson's ratio 0.33, and then we have plastic stress versus plastic strain data. So this is particularly a 2 stress strain curve. So around 269 MPa we have zero plasticity, and then break stress is around 414, and the plastic strain at the break strain is 15%, and the unit which we are going to use is a ton millimeter Newton and second. So let's get started. So we are going to import already meshed model. So we are going to import model. So already mesh model we are importing. Again, this particular model in a contact region we have put a fine mesh, away from contact region we have coarse mesh, and just to have a reference node in center I just put one R3D3 in a center, so we can select a reference point for a rigid body. We have two parts, one is mandrel, other is aluminum part. So just get visualize how they looks. So this is what two parts we have. Now let's start with material data. So already there is some linear data I put, so we'll just edit it. So we have 72 GPa as a Young's modulus, Poisson's ratio 0.33, isotropic elastic material data. Now let's put a plasticity data. On the plasticity data you have different plasticity. We are going to use a plasticity data. So we'll put a yield stress versus plastic strain. Now in Abaqus CAE you can take a data from Excel sheet and you can paste it. So I already put this data in Excel sheet, so I'll just take plastic stress strain data. So I took a plastic data and then I'll just paste it. Then I'll take a plastic strain. So plastic strain at the yield stress is 0, and then break stress is around 414, and the plastic strain is 15.4. So I'll just paste it. So that's it. So we have now elastic. So as a elastic data which is represented by the Young's modulus, and then the plasticity data where we have a plastic strain versus plastic strain data. Now we'll define a section. Now in section we'll define mainly a thickness, 1 millimeter thickness. So we are going to use a shell. It's a homogeneous shell. Now here we'll put a value 1 millimeter. Material is aluminum, and then you say OK. So we define a section property. Now the important thing. So now we are going to put mainly a surface data. So we'll generate a surface, masters versus slave. Now the rigid surface is obvious choice. It will be a master because it's a rigid, and then deformable will be a slave surface. And the mesh is already meshed such a way it is a fine mesh, so that way we may get a converge result out of this. So again I'm going to part. So mandrel, I'll just go to surface. I'll say create, and then I'll say name. I'll give a master surface. So I'll create it, and then I'll just select the part. So I'll just unselect this. I'll unselect this tria. So I'll unselect this. So done. Now once I select all the element, it's showing the two particular sections. So it's a brown or purple surface, internal face. Now guys, here this particular thing is a brown is a S pos. So you have positive vector going out, and the purple is S negative. So the normal is inside. If negative the normal, then it will be a purple, and positive to normal is brown. So we want to have outer brown. So I'll select brown. So we have created a surface, master surface. Now I'll go to slave surface on a aluminum pipe. So we'll say slave, we'll create. I'll just put this everything in one particular view, so that way I can select it. So done. Again S pos, so I'll select a brown. So we have created two surface now. Now guys, till now we updated the metal data. We put a elastoplastic metal data. We have defined a section. We define a two surface. Now we'll get into more into interaction data. So first we'll define a friction property. So I'll go to interaction property. I'll say create, and then you define a friction here. So mechanical tangent behavior will penalty based friction will put. So this particular problem we are putting a 0.3. Then now we'll go and define interaction. So this is particular is what we are defining is a contact. So we'll create. So this is a contact definition. We are going to go for a surface to surface contact in standard. So we'll go there. Now here he say the bottom, you see what the command is asking. It's asking select the region for the master surface. So individually also you can select, but right now we have surface. So I'm clicking on surface. Surface will select master. You can highlight and see it. So this is a master. So we'll say continue. Then for slave type, again we'll select surface, and you see right now I highlighted is a slave already created there. So continue. So this is now we done a surface to surface contact in Abaqus standard, the master and slave. We are going for a finite sliding. Right now we are not going to use any of these parameters, but in next subsequent video we'll discuss each and of every of this parameter and where to use this parameter and advantage. We are saying no edges. Already we have connected a friction property there, so we'll say OK. So now we define a contact. Now I'll just go back just for a second to check what we are defined. So we imported the model, we have material details, we have section detail, we have surface generation, we have given friction, we have define a contact definition. Now we'll define a boundary condition. So boundary condition at the one end we are going to fix, other end we are going to apply a force which is a 270 Newton. So I'm going to BCs I'm creating, so you can give some name, already it is there BC1, so I'm saying displacement. Continue. Now just to save it which time already created node set in a input file already, so that way I'll select enclamp. So this is all bottom nodes. We'll say continue, and here we'll put all clamp conditions. So all translation and rotation degree of freedom is constrained. Then we'll go for a step definition now. So we'll say create, we'll give name pipe bending, static general. Now you can give some description. End time will be 1. NL job we are going to put on because it's a large displacement problem, so it is safer side, put NL job on. Now this is important guys, so you see there is automatic stabilization because this involve a large deformation and contact nonlinearity, material nonlinearity. So this type of problem you can put this automatic stabilization. So we are going to put a automatic stabilization. Now this particular automatic stabilization help us to get a converged result, but also we put a caution here. Whenever you use automatic stabilization, once you get a result out, check how much damping energy is there against the strain energy or total energy. If it is less than 5%, then you should not bother, but if it is more than 5%, then result should be checked carefully. So we have defined a step. Now we given an end time, we have used for stabilization. Now we'll put an increment. So maximum number of increment is 100, which is default. You can put it whatever you want, but it's recommended to have 100. If any problem is not get converged in 100, then you can really go and check and other factors in problem to get a conversion. Initial time step we are going to put it at 0.001. So we are done a step definition. Now we are going for a load, so we'll create a load. This particular load will be a C load, so it will be a concentrated force. So we'll continue. Now already have a node set for force, so already selected the highlighted the force node and force here. So we'll say continue, and here we are going to put 270 Newton on a positive y direction. And the one important thing, because as pipe is going to get bent, the force should be perpendicular to the nodal rotation. So to achieve this, we are going to put a follow nodal rotation. So that way now we are define the load also. Now let's go back and check where we are. So we are done with everything. So importing model, material, section definition, surface generation, friction, contact, boundary condition, and step definition. Now we'll create a job and we'll run it. So we'll say create, and then we'll say XYZ, some job name. We'll say continue. So full analysis, we want to start it immediately. So we'll go to manager. Now let's first write the input file. So let's write the input file. So input file is written. Now this particular file will return into your working directory. For your case it may be a temp directory. I already set this working directory as in C folder, C working directory. So let's go and check how the input. So let's check a input file. So I'm going to check in text pad. So let's go through the input file. So I'll search by star. So stars are commands. So we have node definition for mandrel. We have R3D4 element, then we have one element R3D4 just to have a center. Then we have n set, element set. Then we have this master surface. So you can see whatever I used to say brown and purple. So brown is S pos. So it's a positive normal. Then we have aluminum part, which is S4 R and S4. And then it also have slave surface generation, which is S pos, which is a positive normal side. Then we have instances. Then we have element set and the node set. Then we have rigid body definition. Then we have material data, elastoplastic material data, and then we have friction definition, and then the C load where we are seeing a follower force. We have star static steps. Then we have some stabilization damping we have put. The initial time step is 0.001. Final is full load is applied at 1. Minimum is 1 e power 0.51. And then we have boundary condition at the clamping end. Now guys, one more thing we have missed, which will quickly put it. So we are not put a constraint on the mandrel side. So we'll put a constraint on the mandrel side. So I'll put create BC2, that will be initial step. So displacement will go and put on the mandrel all rotation and translation constraint. So guys, now we are done it. I think the model is right now go for a run. So I'll then submit a run. So I'll submit a run. So run is just started. So let's wait for a result. So right now we have submitted the file for the run. So guys, run is finished. I just uploaded the ODB file. So what you can see right now is a displacement plot. So we applied a force and then starting a bending of this pipe against the mandrel. So let's check the other parameter. How is the plasticity? So I'm going to results. I'll go to field output and we'll see how is the equivalent plastic strength looks like. So there is around 3.78% plasticity is generated here. So let's remove the mandrel element. So now you can see there is a plasticity generated. So the contact region between the pipe and mandrel, that particular part is gone into plasticity. Now also looked into the stresses, how the stresses looks like, one meter stresses. So let's have one meter stresses. So somewhere around a 360 Newton, 360 MPa, the stresses is in the contact region. So that is gone into plasticity. Now just quickly also check how the status file looks like. So that way we'll have an idea how this particular run is gone. So I'm opening the status file. So this is how it looks like. So it started with the 4 equilibrium iteration. There was no severe discontinuity iteration, and then severe discontinuity iteration started at the 9 increment, and then at the end we have 2 severe discontinuity iteration. But overall the model get converged very fast. So that's what actually we want. In when you install a contact problem, you should have quite a good fine mesh in contact region. So you once you define this, then it will go smoothly. So you see it started with 0.001 increment, then it gone to 0.002. So it converged. Total number of iteration in the second increment was lower than the first one. So the load is increased by the 15%. So whenever you see it is lower than the previous one, it started increasing by 15%. So that's how you see it's gone. Every time 15% increment. Now we'll just check other results. Now let's check one important parameter is again we put a stabilization in this particular model. So let's look it into how the energy looks like. So I'm going to go to ODB history output. I'll plot internal energy all IE, and I'll plot static stabilization energy. So whatever dissipation of energy because of damping, that will plot. So this is how it looks. So this is internal energy, and then dissipation energy is quite low. So that way we are confirmed now these particular results are okay. So there is no much dissipation of artificial damping is there. So we can take this result and we can rely on this result. So finally, to overall summary of this particular problem, we done everything. We imported the model, material definition, section definition, we done surface generation, master slave. Master was a rigid surface, deformable was a slave. We define a friction property 0.3. We define a contact surface to surface finite contact with a 0.3 as a friction value. We define a boundary condition. One end was clamp, mandrel was constrained in all direction, rotation and translation. One end we put a force 270 Newton. We gone through a step definition. We run the model. We discuss the result. Mainly we check into into effective plastic strain, and the major thing is whatever stabilization we have put, we check what is the stabilization energy against the overall energy. So that's all guys. So go ahead and run this problem and learn more on a Abaqus contact.